So let's give a comprehensive detail of simple harmonic motion. Now, what is simple harmonic motion? Simple harmonic motion is the motion of a body whose acceleration is always directed towards a fixed point and is directly proportional to its displacement from that fixed point. Now, what can we say about acceleration of a body that is exhibiting simple harmonic motion? So the acceleration of a body exhibiting simple harmonic motion is minus w squared y along y axis. Okay, now this is along y axis if it is going to and fro, up and down. Now we can also look for the velocity of a body exhibiting simple harmonic motion. So we can also look for a velocity that is exhibiting simple harmonic motion. So how do we get that? We already know that y is equal to a, okay, sine theta. The a here, let's see something like this. And if a body is exhibiting simple harmonic motion, it goes up, down, up, down. Now, here is y-axis, okay? And here is x-axis. If we have this place from here to here is amplitude, which is the maximum displacement. Amplitude, which is the maximum displacement. Amplitude is here. Then here is angle theta, and this is y. Okay, so if that is the case, from here to here, we have amplitude. We'll now have y is equal to a sine theta. Okay, and pay attention. If y is equal to a sine theta, we can differentiate it. But before that, we already know that theta is equal to wt. So y is equal to a sine wt. So we can differentiate y to get velocity. So this is displacement, okay, of a body that is exhibiting simple harmonic motion. Now, this particular one is harmonic. Pay attention. It has equal amplitude. Okay, it has equal amplitude, hence it is harmonic, and it is also what? Periodic, because after a cycle it repeats itself and it continues that way. That is why it is called simple, and it is very simple harmonic motion. But we have also what we call damping oscillation. So that is not simple harmonic motion, because the amplitudes for damping oscillation, just like this, they are not the same. You see, this is damping. Damping do not have the same as simple harmonic motion. This is simple harmonic motion. They are up equal in amplitude. The amplitude is equal, but here amplitude decreases. This is called attenuation. It's attenuated. Okay. Now, our point here is to get the exact velocity of a body that exhibits simple harmonic motion. If you differentiate y, you have dy dt, because you are differentiating y with respect to t. Then if you differentiate y with respect to t, we are differentiating sine wt. And if you differentiate sine wt, this w is constant here, then t is variable. So you differentiate wt, you get w. Multiply it by the coefficient a. So you now have a w. Differentiate sine, you get cos. So you have cos wt. So that is settled, and this is the velocity, okay, which is equal to a w cos wt. And again, we have what we call the trigo identity, the fundamental trigonometric what? Identity, which says that sine squared wt plus cos squared wt is equal to 1. And we need to substitute the value we got from here into this so that we remove it and know exactly what we're looking for. So that v is equal to aw into, so what is cos squared theta? So let's look for cos squared theta first. So we make cos squared wt the subject of the formula. So we have 1 minus sine squared wt. But we already know that y is equal to a sine wt. So from here, we can say cos wt is equal to square root of 1 minus sine squared wt. And we can square y. If we say y squared, okay, over a squared, we have sine squared wt. So we can substitute y squared over a squared with the sine squared wt. So sine squared wt is here. So anywhere you see sine squared wt, replace it with y squared over a squared. Now, this v, therefore, becomes aw cos wt is square root of 1 minus sine squared wt becomes y squared all over a squared. So from here, we already know that v, which is the velocity of a body exhibiting simple harmonic motion, is equal to aw, okay, square root of, now what's the other CM? A squared minus y squared, okay, a squared minus y city v, which is equal to aw. Then using solve, we have a squared minus y squared all over square root of a squared. This can cancel out this, and we have b is equal to aw square root of a squared minus y squared all over a. So that we can now say that A cancel out A. Therefore, the velocity of a body exhibiting simple harmonic motion is V equal to W square root of A squared minus Y squared. The velocity of a body exhibiting simple harmonic motion is V equal to W square root of A squared minus Y squared. Now, watch, there is something I want. Asked to find the maximum velocity. Now, maximum velocity can be obtained from where? At V max, comma, Y is equal to 0. Displacement is 0 at maximum velocity. So if at maximum velocity displacement is 0, so from the velocity of a body exhibiting simple harmonic motion, V max can be obtained from there. We have square root of A squared minus 0 squared. So that we have that V max is equal to W square root of A squared minus 0 is A squared. Square root of A squared, this cancel out this, we have A. So this is the velocity, okay, maximum velocity of a body exhibiting simple harmonic motion. Now let's take a very good example on this question, simple harmonic motion. So if we have that the velocity V is given by square root of 16 minus Y squared. Okay, this is the velocity of a body exhibiting simple harmonic motion. Find the amplitude, angular velocity, V max. So to solve this question, we've done. So find the amplitude, angular velocity, and maximum velocity. So the first solution, we record that V is equal to W square root of A squared minus Y squared. We call this equation 1. Then V is equal to square root of 16 minus Y squared. Call this equation 2. Let's compare equation 1 and equation 2. We have that the number 1 solution, A squared is equal to 16. That means A is equal to square root of 16 is 4. Okay? Alright, so 4 meters. Number I is A equal to 4 meters. Then angular velocity is W, II, which is W, and is equal to 1 radian per second. So that is angular velocity. Then V max, which is III, is equal to, at V max, we have WA. So W is what? 1. 1 times 4 is equal to 4 meters per what? Seconds. So that is the solution to the question. Let's take another question. That displacement of a particle is equal to square root of 64 minus V over pi all squared. Now, if we are given this and the question says find the amplitude, find the angular velocity, maximum velocity. So what should we do? First of all, we say that solution. We have to make V the sort of formula from this. So y is equal to square root of 64 minus V over pi all squared. Okay, so transform. Let's transform. Let's transform. So what should we do? Square both sides. You have y squared is equal to 64 minus v squared all over pi squared. So what should we do again? We make v squared over pi squared the solid formula, which is 64 minus y squared. So that v over pi all squared. We take the square root of both sides. So we have square root of 64 minus y squared. So this cancel out this. We have v is equal to pi square root of 64 minus y squared. So this is the correct expression of what we're looking for. So the next thing is to compare. We call this equation 1. Then we compare it to equation 2, which says that v equal to w into square root of a squared minus y squared. Call this equation 2. So we do comparison also such that for number 1, a squared is equal to 64, which implies that a is equal to 8 meters. Number 2, w is equal to pi, then radian per second. Then number 3 is equal to v max, which is AWA, which is 8 pi meter per seconds. So that is how we solve these questions. If this is your first time of seeing my video, like, share, and subscribe to my YouTube channel, as I will take you down to the types of simple harmonic motion. Okay, So let's look at the types of simple harmonic motion. We have different types. We have systems that exhibit simple harmonic motion. But let's look at the first one. The first one is simple pendulum. Simple pendulum. Second one is oscillating loaded spiral spring. The third one is oscillating loaded U-tube. The fourth one is compound pendulum. The fifth one is heartbeat. The sixth one is the piston of gasoline engine. Piston of gasoline engine, and so on and so forth. So if you are given a question, mention 5 types of simple harmonic motion. So you can pick any of these. I'm going to treat simple pendulum, oscillating loaded spiral spring, oscillating loaded compound pendulum. Okay, so for simple pendulum, we have a system that is connected to the ceiling. We connect this bulb to the ceiling, not to the retort stand. When you use retort stand and you do it, if you tap it, it's going to hit the body of the retort stand. Okay, so you don't have free wheel movement. But if you use the ceiling, you connect it to the ceiling. Anyhow you tap it, just allow it to be stabilized. Nothing will obstruct it. So that is one advantage of using the ceiling. So you connect it to the ceiling, and this is the bulb. If you tap it, okay, you will now notice that this bulb will return to this point and goes up again, fall back, goes up, fall back. But at maximum height, okay, at maximum height, there is no velocity. And when there is no velocity, potential energy here is maximum. And when velocity is zero, the particle is at rest. So at rest position is here, when velocity is zero. Now, we have this as the length of the rope, which is this, then this. Then in terms of force, we have tension. We have the tension here, and this is restoring force. Here is tension, here is length, this is restoring force. Then this is returning displacement. Okay, so we have displacement here, and it's negative and it's positive displacement. So y is there. Now, this is the angle of tilt, which is theta. We can extract this and extend this so that this becomes the tension. You draw this also. Okay, as you draw this, pay attention. This is actually showing the weight W, and this shows the FR. Okay, this is the tension, and remember, corresponding angles are equal, so this is the angle corresponding to that, and this is angle 90, the side facing angle 90. So let's bring out this so that you can see clearly. This, okay, let me take it like this, okay, this and this. Now let me put it very clearly. So you see this and this. Okay, so this is the weight, this is the restoring force, this is theta, and this is angle 90. Now from here we can actually get the restoring force. That is our problem here. Restoring force. So how do we get the restoring force? This is opposite to theta. So FR, this is WG, W, which will give us mg. Now when we resolve this to this FR, we have that FR therefore is equal to W sine theta. So that it will be negative because it's restoring. So that FR, if it is absolute value, we have mg sine theta. The absolute value of taking away the negative sign. So this is the restoring force. Acceleration of the body, that is exhibiting simple pendulum. But that of acceleration of the body, exhibiting simple harmonic motion, is A equal to minus W squared Y. Now, from here, we already know that MA is the force, which is equal to minus mg sine theta. So this implies that M will cancel out M, A is equal to minus G sine theta. So that our sine theta will also come out from the diagram of simple pendulum. Okay, so here is y facing theta, and here is the length. So sine theta is equal to opposite over hypotenuse, y all over L. Y is equal to, let's take it as sine theta is equal to y over L. So sine theta is y over L. So A is equal to minus g y all over L. This is acceleration of a simple pendulum. That angular velocity is 2 pi f, which is the same as 2 pi all over period. Now, we can also say that comparing A equal to minus w squared y and A, this is A of simple harmonic motion and this is A of simple pendulum. If you compare the two, you'll find out that minus w squared y will be equal to minus g y over L, such that this cancel out this cancel out this. We have w squared equal to g over L. This implies that w is equal to square root of g over L. But we know that w is equal to 2 pi over t. So 2 pi over t is equal to g over L, which implies that if we take the reciprocal of both sides, if we take the t all over 2 pi, we give us what? Take the reciprocal of this side again, L all over g, which implies that the period of simple harmonic motion is equal to t, which is equal to 2 pi square root of L over g. So this is the period of simple pendulum. Okay, simple pendulum. So that is the period of simple pendulum. If the length is high, okay, it's very long, the time period will be very, very what? Fast. Okay, because t is directly proportional to the square root of length. So t is directly proportional to the square root of what? Length. So as length increases, the time what? Increases. So the square root of length means that when we increase the length, there is time delay. So the time to reach the expected value will increase. And when we decrease the length, it will be faster. Okay. So now, if you get this, you'll now find out that the time delay is long when the length is long. The time delay is short when the length is short. Okay, so this t is directly proportional to square root of what? L. Therefore, t is equal to k root L, and t over root L is equal to constant, which is k, which implies that t1 over root L1 is equal to t2 all over root what? L2. This relation is very important in simple harmonic motion. So let's look out for the next stage, which is oscillating loaded spiral spring. For the oscillating loaded spiral spring, we also connect this to the ceiling, and we have this as the load. Okay. Now, if you connect a load to it, let's make it this way. If you connect a load to this, it will extend this. It will cause an extension. If you add load to it, this is the initial mass when the load has not been added. The moment you add load to it, it will pull it down. Okay, we have a new space or position. This is the initial position, this is the final position. Original point, this is the final position. So there will be extension, which is a change in length. Okay, so we have K here, stiffness. The K that is here is stiffness. The stiffness is stiffness constant, and it is constant for every elastic material. Now, we have that there will be force, which is directly proportional to what? Extension. As you increase the force, the extension increases. So that force is equal to KE. So if it is stiff, you add more force so for you to get what? Larger extension. So that is stiffness, K. Now, we can say that this is from where? From spiral spring. Now, how do we apply it into simple harmonic motion? If you tap it, it will go up and down, to and fro, so that the restoring force will therefore give us negative ky, because it's along y axis. So if that is the case, which is the restoring force, is ma, which is equal to minus ky, which implies that we can make a the subject of the formula, which is minus ky all over m. So from here, you find out that a for a simple harmonic motion is equal to w minus w squared y is equal to minus ky all over m. This cancel this, this cancel this. So we have that w squared is equal to k all over m. And this will give us a special relation between angular velocity and stiffness, k all over what? M. Take note of this. And recall that w has a relationship with period, which says that 2 pi all over what? Period. 2 pi all over period is equal to square root of what? K all over n. Therefore, if we take the reciprocal of both sides, we have that t all over 2 pi, which will give us what? Square root of m all over k. So this implies that t is equal to 2 pi square root of m all over k. That does not end there. Now, when we have the mass of the spring, the initial mass of the spring, and mass of the body that is attached to it. We have T is equal to 2 pi square root of the original mass of the spring plus mass of the what extended body. Now all over K. So we can have this as the period of oscillating loaded spiral spring. Period of oscillating loaded spiral spring. All right. So the next in line is compound pendulum. Compound pendulum, we are actually talking about angular motion. Angular motion. Okay. So a motion whereby the normal displacement, simple harmonic motion, the displacement of normal linear motion will turn to become minus w squared theta, where theta is angular displacement. So we will now say that in this case, the restoring force, okay, wouldn't be just restoring force. Rather, we are talking about restoring torque. We should be talking about restoring torque. In circular motion, the effect seen, observed when a body is turned, okay, is called what? Couple. And now we have torque. When torque is applied, the effect is couple. So this torque is equal to mass here is I. Acceleration is angular acceleration. So torque is equal to I alpha. Now, we need to take note of this. We have noted a torque. To get the restoring torque, we should be talking about torque. This is just torque. Then the restoring torque is negative mgh sine theta. But sine theta is small, so it's equal to theta. So that our torque, which is equal to I alpha, then restoring torque will give us minus mgh theta. So that anywhere we see that this is torque, okay, we now have it as a I alpha is equal to minus mgh theta. So alpha is equal to minus mgh theta all over I. But we have that our alpha, okay, is equal to minus w squared theta. So we have that minus w squared theta is equal to minus mgh theta all over I. So this cancel this, we have w squared is equal to mgh all over I. So that from here, we will now make, say, w squared is equal to mgh over I, square root, this cancel this, which implies that w is equal to square root of mgh over I. Then 2 pi over period is equal to square root of mgh over I, where I is moment of inertia, m is mass of the body, g is acceleration to gravity, then h is the height of the bulb. Now 2 pi over this, we take the reciprocal of the both sides, we now have that t over 2 pi is equal to square root of I all over mgh, which is equal to the period of compound pendulum is equal to 2 pi square root of I over mgh. So this is the period of compound pendulum. Okay, where t is the period, I is moment of inertia. When I is moment of inertia, okay, we now say that mr squared, that is moment of inertia, and is equal to mass. This implies that I, okay, the unit is kilogram meter squared. Okay, kilogram meter squared. Squeeze the camera.